Some people say there's no progress in physics. I'd never say such a thing, of course, because there's just been a major breakthrough on a 125-year-old problem, David Hilbert's famous sixth problem. This breakthrough unites three of the most important theories in physics, and it also shows how irreversible behavior emerges from time-reversible laws. That's a big deal, even though that breakthrough came from mathematicians, not from physicists. Physicists were busy redefining the kilogram again, or whatever it is that we do now. But let's have a look. Before we talk about mathematicians who revolutionized physics, a big thank you to all my supporters, especially those in Patreon tiers 4 and higher. This channel would not be possible without your help. And you can help me too, either on Patreon or by joining this channel right here on YouTube. Now about Hilberts Problems. In the year 1900, the mathematician David Hilbert presented a list of 23 unsolved problems which he thought should guide mathematical research in the 20th century. Some have been solved, some remain open, and some are so vaguely formulated that we're still arguing about what it would even mean to solve them, but one of the most ambitious ones is number 6. Hilbert asked for an axiomatic foundation of physics. In other words, he wanted physicists to stop making things up and instead derive the equations they use from well-defined assumptions. If that could be done, it'd solve one of the biggest puzzles of our existence, that is, why time passes in only one direction. Because on the level of atoms, forward in time works the same way as backward in time. Yet this is clearly not the case in our everyday life. So how does that happen? Yes, you've been told it's to do with entropy increase, and that's probably correct. But it's never been proved for the laws of physics that actually describe atoms. And that was Hilbert's point. Stop making up plausible explanations. Derive them. Hilbert mentioned that a good place to start with this sixth problem would be to understand how the equations of fluid dynamics arise from the motion of atoms. Fluids, after all, are made of particles, and in principle, we could just track every single molecule. But there are way too many of them. Instead, physicists use 3 different theories depending on the scale they look at. At the microscopic level, particles follow basically Newton's laws and bounce off each other. At the intermediate level, or mesoscopic level, we don't care about each particle, just the statistical average. That's described by what's called the Boltzmann equation. And at the macroscopic level, we have equations for the flow of air and water, the Euler and Navier-Stokes equations. Each of these descriptions works in its own regime, and we expect that the higher levels can be derived from the lower ones. But Hilbert asked, well, where's the derivation? That's what the authors of the new paper did. It's a fairly long technical paper, hasn't been peer-reviewed, and I admit that I don't understand the details, but it plausibly looks like they actually solved the problem. They show that if you take a large number of tiny hard spheres, all bouncing around in a box, and let them follow Newton's laws, then as you zoom out, you first get the Boltzmann equation, and then you get the equations of fluid dynamics. This was previously done approximately for short times, but the difficulty that they overcame was to extend the short time result to longer times. For this, they developed a clever way of tracking and classifying all possible collision histories and then evaluating their probabilities. In some sense, it's a straightforward calculation, devil's in the details. I actually find this a very impressive result. Why does this matter? For one thing, it justifies the equations that we use every day in engineering, weather prediction and aerodynamics. We now know they aren't just good guesses, they follow from the underlying laws. But maybe more interestingly, this shows in detail how irreversible behavior can emerge from reversible laws and why time has a direction for us. It's like the first step to answering Isaac Asimov's last question: how can we decrease entropy? that I think is the ultimate question that any living being in this universe will eventually ask. That and when did my joints begin making this sound? But as impressive as this breakthrough is, it doesn't entirely solve Hilbert's sixth problem. That it also include quantum mechanics, relativity, turbulence, and the question of how to get cheese to stick to the pizza when you cut it. So no, the problem hasn't been solved, but a piece just clicked into place. On the bullshit meter, this gets a 0 out of 10, even if it's wrong. It's serious and deeply offensive to the physicists who take great pride in making things up that sound reasonable. Every time I use ChatGPT, I feel a little bit dumber. I think it's not my imagination because there have been several studies now that document just how AI assistance negatively affects our cognitive function. But it's okay, I guess, because soon enough we'll be too dumb to notice. In a truly eye-opening study that just appeared, researchers from MIT Media Lab recruited 54 university students and had them write essays, either entirely on their own or with internet search or using GPT-4o. While the students were working, the researchers recorded their brain activity with EEG, and later the students had to answer a bunch of questions too. The findings were remarkable. A whopping 83% of participants in the AI-assisted group could not accurately quote any text they'd just written. In the other groups, it was merely 11%. Also, the measures of brain activity were roughly half as strong in the group of GPT users than in that with the unaided writers, with the search group in the middle. The writing performance too was noticeably different. Essays written with the help of GPT had a lot of word clusters that repeated and markedly less variety in phrasing and sentence structure. But the maybe most damning finding was that after 3 sessions of this, the researchers switched the AI-assisted group to no assistance, and their performance remained bad, even though they now had to write on their own. 78% still weren't able to quote anything they'd written, and their brain activity still lacked the synchronization normally associated with this task. The researchers call this cognitive debt. Basically, they'd become used to not using their brain. This comes after a study from Microsoft last year that showed that users who rely on AI use significantly less critical thinking. Yes, AI use has been linked to some positive effects, but even those turned out to be a double-sided sword. For example, last year, researchers from the University of Houston in Texas found that using large language models for brainstorming gift ideas does significantly increase the creativity rating of these ideas, according to humans. However, a follow-up study that just appeared points out that using AI also significantly reduced the variety of ideas, which makes you suspect that in the long run they'll also be considered as less creative. AI-assisted ideas seem creative now because they're unusual for humans, but in the long run it'll just be the same thing over and over again. A similar finding was already reported last year when researchers had about 400 people write short stories with and without the help of AI. The AI-aided writing was rated more creative, but the stories were also more similar to each other. Nevertheless, students for sure like using it, and educators on the front line report worrying developments. Students increasingly seem unable to read and comprehend long text as they're used to feeding it into AI and just getting a summary. A typical report comes from Andrew Tobolowsky, a professor in the United States, who told the Chronicle of Higher Education, "When I have students respond to passages of various kinds in the classroom that I didn't assign at home, many struggle or seem to struggle to arrive at any real takeaways, even so far as what literally happens over the course of the text. A writing teacher quit because she found herself grading AI-generated papers more often than not. Students, often by their own admission, dump the prompt into ChatGPT and hand in whatever it it spits out. And because that's too obvious now, they instruct the AI to sound dumb or add typos by hand. What are we to make of this? The demise of human intelligence with the rise of new technologies has been declared many times with TV, with video games, with the internet, and so far we've survived. That means we should take these worries with some grains of salt, but it doesn't mean this time won't be different. AI, like none of the other tools before, saves us thinking time, and we all like being lazy. This makes me think that we might have to become more deliberate about brain training. Much like today we go to the gym, or at least sign up for it, I suspect that in the near future we'll see dedicated services that aid thinking performance, or at least we'll sign up to them, and they'll probably be run by AI. Chinese companies have come with a flurry of announcements in quantum computing just in the past month. IBM should be worried, one headline said. US intelligence community veteran warns about China's quantum computing progress, reads another. Brad Smith, president of Microsoft, warns that the United States cannot afford to fall behind, which, according to CNBC, is because then banks might not be able to keep transactions private. That sounds very alarming. I've had a look. End of last year, researchers from the University of Science and Technology in China in Hefei announced that their quantum computer, Su-Chongxi 3, which works with superconducting circuits like those of Google and IBM, is on par with Google's Willow chip that has about 105 qubits. That's when Americans began to panic, but that was only the beginning. In May, the Chinese company Origin Quantum announced Tianji 4.0, a quantum computing platform that should be able to work with more than 500 qubits. And that you see here in this alleged photo of a photo that someone's taking of a model of the computer. Global News reports that the company's director, Guo Ping, told them that the company has already run over 380,000 tasks for more than 26 million users all over the world. Honestly, that's really impressive. It's a lot more than I'd have expected. 26 million users of a quantum computer that can't do anything useful. But are these numbers remotely plausible? 26 million users ran 380,000 tasks. That's like 68 users per task. How many users do you need to run a quantum computer? 1 to calculate the result on their phone and 67 to write a press release? I call bullshit on this. But just in case, if you're one of those 26 million, go and check out my quiz platform. You can actually use it. Then again, I'm just some random YouTuber, so what do I know? Better listen to the experts. I mean, what about this headline? IBM should be worried. Turns out that this quote comes from no one. They just put quote marks around it because I don't know why. The worried US intelligence community veteran is now CEO of a company that sells protection from quantum computers, so maybe not the most unbiased source. And the claim from CNBC that banks might not be able to keep transactions private is wrong, because we do have protocols that can't be cracked even by quantum computers. This is called post-quantum cryptography, and financial systems are already in the process of switching to those. Okay, but it's not all hot air, I think. The biggest announcement came just last week when a Chinese research center announced plans for a quantum computer that, they say, will reach 5,000 qubits, called the EasyQ Engine 2.0. For context, IBM already last year announced a chip with somewhat over 1,000 qubits called the Condor chip, and just the other week I told you about their plans to scale this up to some 100,000 qubits, though we haven't actually seen those plans. We also haven't seen any evidence that IBM can even control these 1000 qubits, or that anyone can for that matter, because it's one thing to lump together qubits on a chip, another thing entirely to actually do something with them. Another supposed Chinese advancement that was just reported is that China pushes quantum computing towards industrial use. For example, with hybrid quantum classical use for image analysis. Again, that sounds good, but a general problem with these hybrid quantum classical uses is that you don't actually need the quantum part. It's like saying, look, this teleprompter's basically a beam splitter, so this is a quantum video. Not a joke. The teleprompter works with a semi-transparent glass that's basically a beam splitter, just not at lab quality. But I digress. What I meant to say is that most of these hybrid quantum classical calculations are about as quantum as iron. The bottom line is that we still haven't seen a solution to the problem of how to scale these devices to a size at which they'll be better than a conventional computer at something useful. Why the Chinese are throwing money at this is anybody's guess. Maybe just to piss off the Americans, and really, who can blame them? Physicists just invented a new type of particle accelerator using a micro nozzle. It accelerates protons like the LHC, but does over a distance of millimeters what takes a standard magnet-based accelerator hundreds of meters. In the press release, the inventors say that the new method delivers excellent beam quality. Could this be the future of high-energy physics? Let's have a look. For decades, building a proton collider meant increasingly larger rings of increasingly stronger magnets. It's worth the effort, we've been told. Probing short distances requires high energies, and particle colliders therefore are our best chance to find out what happens at short distances. Yet the increasingly huge size of these colliders has become economically unsustainable. CERN's plans for the next larger collider, the FCC, which would be more than 90 kilometers in circumference, are in the range of about $40 billion. One of the technologies that could shrink particle accelerators down is wake field acceleration. For this, one shoots with a laser at a gas. The laser displaces charges and creates a plasma that travels at high speed, pulling electrons behind it. This method has been used to successfully accelerate electrons up to about 5 gigaelectron volts or so over a distance of about 1 centimeter. That's still about a factor 1000 less in energy than what the LHC currently delivers, but it's promising. Unfortunately, wake field acceleration only works for electrons. Protons are just too heavy. This is where the new idea comes in, which they call micro-nozzle acceleration. It works like this. Inside a vacuum chamber, you place a metallic funnel. That's the nozzle. It's just a few millimeters wide, and in their example, it's made of aluminium. Inside of it, you have a small rod with hydrogen, because you want to accelerate protons, and hydrogen nuclei are just protons. The rod could be frozen hydrogen or some other material that's saturated with hydrogen. Then you take a big laser, it must have a power of several petawatt, and shoot at the funnel. This rips electrons off the material of the nozzle. At the incoming side of the nozzle, this creates a lot of moving electrons inside of the nozzle. These hit the hydrogen rod and kick out protons. But at the outgoing side of the nozzle, this strips electrons off on the outer side. This means that the inner side is positively charged. Because of the curve of the nozzle, this both focuses and accelerates the protons. This is really clever. Now I have to warn you that this was not an experiment. It was a computer simulation. But at least in this computer simulation, the protons reached almost a gigaelectron volt in energy. So that's still somewhat less than wake field acceleration reaches for electrons, and it's a simulation rather than the real thing. But come on, this is a really cool idea. And they reached this acceleration just over a few millimeters, which coincidentally is just about the size of my enthusiasm for the $40 billion collider. But Just like wake-field acceleration, this method needs a multi-petawatt laser, and those are neither small nor cheap. They're typically 10 to 20 meters long. That's still much less than the LHC pre-accelerator, which brings protons up to 1 GeV2, and that's about 100 meters in diameter. But you see, for this energy, the difference in size isn't all that dramatic. The big question is therefore whether and how these different methods, wake field and micro nozzles, could scale to a TeV or beyond. And what about the excellent beam quality? Wake field accelerated electron beams now routinely achieve a focus angle below 1 degree and energy spreads of only a few percent. In contrast, the simulated proton beam from the micro nozzle has an opening angle of about 16 degrees and an energy spread of roughly 50%. That's not what particle physicists will call excellent beam quality. The reason the authors say this, I believe, is that the micro nozzle idea isn't entirely new. There have been earlier attempts to accelerate protons by shooting with lasers at things, and this new method is excellent compared to those. Everything is relative. Why does this even matter? Proton beams have various applications. For one thing, they're being used for cancer treatments because their energy can be deposited in tissue in a more targeted way than X-rays. However, the size and cost of the required proton accelerators makes this therapy method impossible for broad applications. Proton beams can also be used to treat or probe materials. And of course, what we really want is particle accelerators that exceed the collision energy of the Large Hadron Collider to test the fundamental laws of nature, to find some anomalies to argue about, and to keep theoretical physicists away from Wall Street. Thanks for watching. See you tomorrow.